Hello students, in this video we will study about the alpha particle scattering experiment and the Rutherford's nuclear atomic model. The alpha particle scattering experiment it is conducted by Ernest Rutherford in 1909 and it was the groundbreaking experiment which changed our understanding about an atom. This experiment provides the first evidence that as an atom consists of small, dense and positively charged nucleus at its center. So before beginning into the details of the alpha particle scattering experiments, let us understand what is an alpha particle. The alpha particles are type of ionizing radiations, so which consists of two protons and two neutrons. So alpha particle is identical to the nucleus of helium 4 atom because since they are not carrying any electrons, the alpha particles are positively charged. So in concise, the properties of alpha particles are its composition is two protons and two neutrons, and therefore the mass is approximately 4 atomic mass unit, and the charge of alpha particles are +2. Then how did these alpha particles are produced? These are produced during the alpha decay of heavy unstable nuclei. So in alpha decay, one parent nucleus it ejects an alpha particle by and transfers into two different elements, or we can also say two daughter elements. And the daughter element, the atomic number of the daughter element is reduced by 2 and the mass number is reduced by 4 because the alpha particles composition is two protons and two neutrons. Then comes into a brief history about background of the atomic model. The before Rutherford's experiments, so the widely accepted atomic model was the plum flooding model, which is proposed by the J.J. Thomson. So this is according to this model, the atom was composed of a diffused cloud of positive charge, and where the negatively charged electrons are embedded within it. It was like the sliced watermelon. So after this, the Rutherford he was conducting an experiment, and the setup was the Rutherford along with his two assistants, that is Hans Geiger and Ernst Marsden. They have designed these experiments where a stream of alpha particles it is directed at a very thin sheet of gold foil. So around the gold foil they placed a fluorescent screen, so which acts as a detector, which is coated with the zinc sulfide. So when an alpha particle it is struck with the screen, so it produces a tiny flash of light. So and these lights can be observed by using the microscopes. Fine. So this is the experiment. A radiation source is a source of alpha particle, and it is directed towards the gold foil. And what are the expectations of the experiments? So based on the plum flooding model, Rutherford and his team expected that the alpha particle should pass through the gold foil with a minimal deflection. That is because most of the positively charged protons they are thought to be spread out across the entire atom. Okay, so that's why most of the alpha particles should not deviate or should not scatter, they just pass through the atom. If we have a visual experiments of that one, is like assume that this is the atom where blue dots are the positively charged protons or positively charged particles. So when the alpha particles are streamed towards these positively charged particles, this was the expectation because based on the J.J. Thomson's atomic model. When we trace the tracks of the alpha particles, it should be always be in the straight line as it is seen in this particular video. Okay, but what is Rutherford's analysis? What he found is, again when comes back to the previous slide. So here in the Rutherford's there is an unexpected deflection by a small number of alpha particles through these Rutherford's experiments. So when these small number of deflection happen, again we'll just see it in terms of the animation. So here these are the nucleus, and at the center we have the nucleus, and these are the atoms. At the center we have the nucleus. When alpha particles are bombarded with this thin gold foil, so here the atom, the protons are 79, that is atomic number 79 means it is gold again. So these are all the alpha particles. So you can carefully observe this. I'll just on the traces of the alpha particles. So the alpha particles which comes near to the nucleus, that is the center dot, then there is a deviation in the alpha particle. So the alpha particles which are come very much closer to this nucleus deviates heavily, but the alpha particles which are not comes as much close, then their deviation is slightly lesser compared to the others. So this is one good expectation or one observation that is found in the Rutherford's experiment, alpha scattering experiment. So based on these observations, he has analyzed the results or observations. So what's his analysis is, he concludes that most of the atom is empty, because majority of the alpha particles, they are just passed through the foil without any deflection. So therefore the Rutherford concludes that the atoms must be very largely empty space. And then its second analysis is, the atom has small, dense and positively charged nucleus. That is again based on the, it's a large angle deflection by an alpha particle. So that suggests that there must be a very heavily positive charge which is situated at the center part of the atom with a very small volume. So this central core, he called it as a nucleus, where nearly all of the atomic mass resides in it. And the third analysis that he has observed is, the electrons, which are negatively charged particles, they are much deflected by the, they don't have much influence on the alpha particles. So therefore these electrons are relatively at a larger distance from the nucleus. So these are the main features or analysis of the Rutherford by the observation of alpha particle experiment. So when we plot the number of scattered particles with respect to their scattering angle, this graph typically shows that the majority of the scattered particles are undeflected. When you observe the scattering angle, which is on the x-axis, and the number of scattered particle, which is on the y-axis, you can see almost more than a million of particles have a small deviation, and almost a backscattered or 180 degree scattered, or the heavy deflections, you may say more than 120 degree, the number is less than 100, means 10 to the power of 2, less than 100. So therefore the number of alpha particles which are deviated heavily or backscattered is much smaller, and most of the alpha particles are just passed through the atom. And the reason for the deflection of the alpha particles is again based on the Coulomb's force. That Coulomb's force is again given by the equation, that is F equal to 1 upon 4 pi epsilon naught 2E into Z by R square. Again the 2E is for the alpha particle and Z is for the nucleus. It's basics Coulomb's equation. And hence Rutherford suggested a new nuclear model, that is called as Rutherford's nuclear model. The key features of the Rutherford's nuclear model is, one is nucleus, which is very small and dense, because the this nucleus occupies a small fractions of atom's volume, which is almost when you compare the volume of a nucleus with respect to volume of an atom, it's almost 10,000 times greater. And the nucleus is again, it's a positively charged particle. The nucleus contains only the protons and the neutrons, and neutrons are the neutral particles, and hence nucleus as a whole is a positively charged, and the electrons which are orbiting around the nucleus, they balances this positive charge by carrying the negative charge. And the next one, electrons. So the orbit of electrons, they move around the nucleus in a circular orbit, and which is almost similar to the planets orbiting around the sun. So therefore Rutherford's nuclear model is also called as the planetary model of a nucleus. And the electrons, these are held in these orbits by the electrostatic force of attraction between the positively charged nucleus and the negatively charged electrons. And the electron clouds. So although Rutherford's model depicted that electrons is in definite orbit, but this idea will later evolve into a different concept called as the electron cloud. Okay, and the next one is atoms stability. Rutherford's model could not explain the why the electrons are why electrons should not lose energy and spiral into the nucleus, and they don't collapse into the nucleus. This is, atoms are very stable, but Rutherford's nuclear model couldn't able to explain this one, and this is one of the limitations of the Rutherford's nuclear models also. And one more key feature, that is this, most of the volume in the atom is an empty space. And as I already told you, when it comes to the limitations, Rutherford nuclear model unable to explain the electron collapse problem, and it doesn't explain one more thing, that is atomic spectra, because these atoms can produce the spectral lines, but Rutherford's atomic model, or sorry, nuclear model couldn't able to explain that. And when it comes to one more limitation, that is collapse of a matter, that is, according to the classical physics, the orbiting electrons should continuously emit the electromagnetic radiation when it is revolving around the nucleus. So as it emits the radiation, it should lose the energy, and eventually it just fall onto the nucleus, which leads to the collapse of an atom, entirely atom. But in practical, this is not happening. So Rutherford's nuclear model couldn't able to explain why the nuclear collapse of an atom is not taking place. So this is one big limitation from the Rutherford's nuclear model. And as we observed in that earlier, the alpha particles have some trajectory. So the trajectory when it is traced, so it completely depends upon the impact parameter, that is B, which is also indicated by the small b, impact parameter. So this impact parameter, it is basically the perpendicular distance of an initial velocity vector of an alpha particle. This is the initial velocity vector, initial velocity vector of an alpha particle from the center of the nucleus. Okay, so the fact that the only a small fraction of these number of incident particles, they can rebound back or they deviate much. Otherwise, most of the alpha particles are just passing through the atom without any deviations. And when it comes out to be the electron's orbit, the Rutherford's nuclear model of an orbit pictures is atoms as an electrically neutral sphere, where a small massive positively charged nucleus is at the center, and the electrons, which are negatively charged particles, are revolving around the nucleus, and hence atom as a whole is a neutral particle. Then these orbits, the electrostatic force of attraction, that is Fv, how this is balanced, the positively charged electron and the negatively charged electrons and positively charged nucleus, although they are unlike charges, how they are balanced. So this is explained like with this equation, the electrostatic force of attraction, that is Fe, between the revolving electrons and the nucleus, so it should balances by the centripetal force, that is capital Fc, to keep both of these, or to keep the electrons in the orbit. So therefore, when we take the equations of these electrostatic force and the centripetal force, we have to equate it. So that is 1 upon 4 pi epsilon naught E square by R square, which is equal to mv square divided by R, that is the centripetal force. And if we solve this equation for the orbit's distance, that is small r, which is equal to E square divided by 4 pi epsilon naught m into V square. So again, in these equations, m is the mass of an electron, v is the velocity, e is the charge, and r is the distance, orbital distance or diameter, we may also say. Next, the kinetic energy of the electron in an hydrogen atom, we will take a small simple one. In an hydrogen atom is given by k is equal to half mv square, which is equal to E square divided by 8 pi epsilon naught into R, and the potential energy is given by capital U is equal to minus E square by 4 pi epsilon naught R, and hence the total energy is given by potential energy plus kinetic energy, so which is equal to this equation, that is E square divided by 8 pi epsilon naught R minus E square divided by 4 pi epsilon naught R. Hence, after simplification, the energy equation is given by capital E is equal to minus E square divided by 8 pi epsilon naught R. So by using this equation, we can able to calculate or estimate the energy of an electron in this particular orbit at a distance of R. So hence, these are the small brief explanation about the alpha particle scattering experiment and Rutherford's nuclear model of an atom. For more information, just join our WhatsApp channel by scanning this QR code, and or else you can contact either through email or phone number. Thank you.